Greetings, everyone, and welcome to the I1 webinar, First Results from 3 Years of GNSS Interference Monitoring from Low Earth Orbit, published in the winter 2021 issue of Navigation. Today's webinar is being presented by two of the paper's authors, Dr. Todd E. Humphreys and Dr. Lakshay Narula from the University of Texas at Austin. Dr. Lakshay Narula received his PhD in electrical and computer engineering at the University of Texas at Austin and is an applied scientist at Amazon Lab 126. His research interests include PNT security and robust state estimation and sensor fusion for automated vehicles and robots. Dr. Todd Humphreys received his PhD in aerospace engineering at Cornell University and is a professor in the Department of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin, where he directs the Radio Navigation Laboratory. He specializes in the application of optimal detection and estimation techniques to problems in secure, collaborative, and high-integrity perception, with an emphasis on navigation, collision avoidance, and precise timing. We greatly appreciate the time and work our presenters have put into the webinar today. Following their presentation, we'll take questions. If you'd like to ask a question, you can click on the Q&A box in your viewer, and you can type your question in at any time. So thank you for being here, and now we'll turn it over to Lakshay and Todd.
Hello, everyone. We're coming to you live from Austin, Texas, and Lakshay from sunny Northern California. I'd like to first take some time to recognize my other co-authors besides Lakshay. Matthew Murrian is the first author of this paper and did the yeoman's work in developing models for estimating the location of emitters on the ground and did quite a bit of the writing. Peter Iannucci is a postdoc in my laboratory and contributed to some of the implications for GNSS receivers. Scott Budzian is with the Naval Research Laboratory and was our main contact there in managing the instrument we have on the International Space Station. Brady O'Hanlon, while he was working at Cornell University, was instrumental in getting the instrument placed on the International Space Station. Mark Psyche, now at Virginia Tech, formerly at Cornell, also did some work with the paper to validate the analysis that we have done. Anyway, I'm pleased to have been able to write this paper with so many great co-authors. Our outline for today follows the basic flow of the paper. The point of today's seminar is not really to develop everything that's explained in the paper. Instead, what we'd like to do is invite you and interest you through this seminar into reading the paper. So as they say, the book is better than the movie. Our motivation starts back in 2011. If you want to ask where deliberate wide area persistent unauthorized GNSS interference has occurred, I believe maybe one of the first examples of this was on the border of North and South Korea in 2011. Now remember, plenty of interference occurs all the time. These are government sanctioned tests or not very persistent accidents, etc. But when we're talking about deliberate wide area persistent unauthorized interference, these are more concerning. And since 2011, there have been many more of these events. For example, in the same area near North and South Korea, we have in Shanghai in China and in Eastern Russia, some events that have been more recent. Over toward the west, we see events in the Mediterranean, the Black Sea, Moscow, Northern Scandinavia. These have become quite a problem. The event starting in 2011 has led to many more, and now this is a concern that covers the globe. One of the most interesting sets of activities occurred in the Black Sea, starting in around 2016 and continuing even quite recently. What we saw there in some work that I did with the group C4ADS was that ships in the Black Sea were showing up at airports according to their AIS beacons. Some ships were even spoofed all the way to airports in Moscow. This was puzzling, and we put together a pattern of analysis that showed that this could be traced to visits of the Russian head of state to this area. Apparently, his security detail was concerned that he might be subject to, say, drone attacks, and so these spoofing attempts were to thwart such attacks, to ward off the drones. This kind of deliberate spoofing activity caught our attention. It was intriguing, and so we wondered if we could examine it further. The full report of this analysis you can find in this nice report called Above Us Only Stars, written by C4ADS. So we had an opportunity to think about how global interference, persistent interference, could be examined more readily. Putting boots on the ground, finding every emitter is not practical. But looking at it from space could be very valuable. Space-based GNSS interference monitoring was not really explored by 2018, at least in the open literature, but it has the potential to offer a wonderful coverage, continuous global situational awareness and interference characterization. And it just so happened that we had an instrument in 2017 placed on the International Space Station. This instrument was the culmination of years of work, mostly at Cornell University and the Aerospace Corporation and the Naval Research Lab, to put a science-based GNSS receiver, a software-defined receiver, on the International Space Station. You can kind of see here the receiver's antenna plate with 3 separate antennas. And inside this crate is where the receiver resides. It's called the photon receiver, and it's a fully software-defined receiver. It's dual frequency, L1 and L2. As a pure software-defined receiver, that means that all digital signal processing is done in a general purpose processor, as opposed to, say, an FPGA or an ASIC. One of the salient features of this receiver is that it can record raw intermediate frequency data at about 6 megasamples per second on both L1 and L2, and then we can ship those data down in small, say, 60-second snippets for processing on the ground through the NASA backbone. So this opportunity met our intrigue over the various interference events that were popping up around the globe, and we realized that this science-grade receiver might be used to better understand those interference events. Now, the science-grade receiver has a day job. It was built to do ionospheric sensing, like many other LEO GNSS receivers. It was built to examine the ionospheric content, the total electron content in the upper atmosphere, and to examine, say, thermal profiles or precipitable water vapor in lower atmosphere. We were looking, the original intent was to exploit its software-defined nature so that we could downlink these wideband signals to the ground and do forward-backward processing and get deeper down into the atmosphere. But because of its flexibility, it also offered us a chance to examine interference events around the globe. So back to this situation in the Black Sea. It's around 2018, and we're interested in asking the question, would the Black Sea spoofing be detectable in the raw intermediate frequency samples that we capture via the photon on the International Space Station? That was really what precipitated this paper. And thankfully, we had done some captures where we had recorded wideband data on 3 separate days that were not too far from the Black Sea. So we could look at historically at these data and determine whether any of the spoofing signals that were active at the time, and we showed that they were active at the time that these overflights occurred, could be picked up by the photon sensor as it was flying over and looking back toward the Black Sea. So we recorded these data, we shipped them down through the NASA backbone to the Naval Research Laboratory, and from there to UT Austin, and we processed these 60-second raw sampled chunks using the latest version of our software-defined receiver, which we call GRID. So we weren't actually even using the software-defined receiver on the International Space Station. Instead, it was just being used to capture the raw samples and send them down. And that way we could use the most recent version of our receiver on the ground and even do more fancy processing that would be possible on orbit. Our first signal analysis, once we got the data, revealed that yes, something was definitely up with these signals. The power spectra you see here are for L1 in the left-hand column and for L2 in the right-hand column. Now, to compare against a nominal case, have a look at the lower cells here. This is a 3 megahertz block for L1 and 3 megahertz for L2, taken just off the coast of Portugal over the open oceans where things are nice and quiet. On the other hand, for these 3 days, you see rather different waveforms at L1 and something fairly narrow band but persistent at L2. What you see at L1 not only has some narrow band elements, but it has a wide band component also. And this one is especially intriguing. On day 144, there was an extra wideband component that sort of came and went. It waxed and waned in time over the 60-second capture. So definitely, yes, we were capturing something anomalous in these signals. Here's an example of that second day's capture. You can see this center prominence coming and going. Even to this day, I'm not sure how to explain this, what was going on with the transmitter, the interference source, why they were transmitting this, etc. Now, the mystery got deeper as we started tracking the data using our ground-based software-defined receiver. We had to alter the signal, alter the receiver so that we could track these signals. We put it in a special mode so that it was willing to continue tracking the signals, even though it discovered that the signals were not modulated with any navigation data modulation. These signals you see here are GPS L1CA signals modulated with PRN codes common to many of you on this call, or familiar to many of you on the call. But the 50 bits per second or 50 hertz navigation data was absent. It was as if these signals were never intended to be used for spoofing or for navigation. Instead, they seem to be more for a denial of service. In other words, these were meant to knock receivers off of GPS tracking of the legitimate signals, but they weren't capable of fooling receivers because they lacked the navigation message overlay. So we call this coded jamming, in that it's using a PRN code. In fact, it used almost all of the PRN codes for GPS satellites from 1 to 32, but it did not overlay them with the LNAV modulation. So that increased our, increased the intrigue. That's a puzzle. I'll get back to that in just a bit. Also, as part of our software-defined radio processing, we're able to generate data-wiped 100 hertz IQ accumulations. So these are the raw products of the correlation operation inside the tracking loops of the receiver. An authentic signal on a clean day, say off the coast of Portugal, looks like this lower panel here. The I is in black and the Q, the quadrature where the noise resides, is in gray. The tracking you see here is beautiful. No chance of cycle slipping, high carrier to noise ratio. The authentic signal as received during overpasses with the interference that we were targeting in the Black Sea looks more like this. You can see that there is more noise in the quadrature channel, and the carrier to noise ratio has been reduced. The I is closer to the Q, is closer to 0. However, what's exciting is that we were able to track these coded jamming signals in such a way as to separate their I and Q correlations, which means that we didn't experience any cycle slips. We're able to track the carrier of these signals with no cycle slipping. We're not sure what these fades are, which appear to be non-natural. This is not something that comes out of the space or the Earth to space environment. This appears to be something built into whatever transmitter is being used. So the key point here is to recognize that these signals, having been caught and tracked by a GNSS receiver, allow us to extract the carrier time history. And this opens up the possibility of locating the source. That's the next section here. So if we can track the carrier, then of course we can get the Doppler time history. And this chart here shows the Doppler time history over about the 60 seconds of one of the day's capture. Now, anyone who's familiar with the history of GNSS might look at this and say, oh, that's very much like the original transit system that predated GNSS, where Doppler was used to locate submarines on the Earth's ocean surfaces. In a similar way, but kind of the problem flipped on its head, you can use the Doppler time history from a known location, in this case, the International Space Station, with known timing, to infer the position of the transmitter. In this curve you see here, there is plenty of information about the position of the transmitter if you assume the transmitter's on the surface of the Earth. Now, the information is revealed in the equation you see down below. The transmitter's location is part of this unit vector, whose transpose gets multiplied by the velocity of the receiver. Now, we know the velocity of the receiver because we were able to track enough authentic signals during the time of this 60-second capture that we got not only the velocity of the International Space Station, the receiver, the photon on the ISS, but also the timing and timing rate of its clock offset. So VR is known to us. Of course, the wavelength is known to us. The speed of light is known to us. Del T R dot is known to us. Things that are not known are embedded in R hat and also del T T dot. This is the transmitter clock error time rate of change. And you can see that this del T T dot has a lot to do with the ultimate Doppler frequency. So if this is changing a great deal, in other words, if the transmitter's clock is unstable, then our ability to estimate the transmitter's location will be somewhat masked, the location being here and the transmitter instability would be manifest here. So it's not cut and dry. Maybe we can estimate the location of the transmitter accurately if it's using a good clock. We won't be able to estimate it so accurately if it's not using a good clock. And Matthew ran a bunch of simulations to determine exactly what penalty would be paid for increasingly worse clocks in the transmitter. He found that a clock that is characterized by these sort of numbers for one of its Allen variance parameters, say an OCXO, would only have around 67 meters of error contributed just because of the clock instability, whereas a TCXO, a temperature compensated crystal oscillator, might have up to 7 kilometers of error. In any case, even if it were a low budget TCXO, 7 kilometers of error would still reveal something rather interesting about the location of the transmitter. And so we were eager to proceed after having done this analysis. In the event, we were able to get post-fit residuals for the Doppler time history. And so this is after we estimate the location of the source. Then we can take a look at the post-fit residuals of that Doppler model that I showed you earlier. And we were able to find that our post-fit residuals were actually quite good with a standard deviation of only a couple of hertz. This indicated to us that the clock was fairly stable within the transmitter, and that whatever transmitter was being used was stationary during the time of our capture. A further analysis allowed us to estimate the Allen deviation of the transmitter. We did capture on multiple days, and so we looked at the clock, estimated clock offset rate of change on these days, and determined that the clock appeared to be consistent with an OCXO, an oven-controlled crystal oscillator. And so this gave us a sense that, oh, if we're able to locate the source, we'll have done so fairly accurately because they're using a decently stable clock. Anyway, back to our mystery. How could these coded jamming signals, which lack navigation data modulation, be spoofing GPS receivers in the Black Sea? We know that the receivers in the Black Sea were being spoofed because their positions, as manifest through their AIS beacons, were showing up all over the place, on land, near airports. So the AIS beacons are being fed by GPS receivers on board these ships. It was definitely happening that these receivers were getting duped, and yet the signals we were capturing over the Black Sea were not capable of doing this. They didn't have the necessary data modulation. None of these GPS receivers, no GPS receiver would have been fooled by these signals. They could have been jammed by them, but they wouldn't have been fooled. Well, then how to explain everything that was going on in the Black Sea? The answer we found was that the coded jamming signals were not, in fact, coming from the Black Sea region. We were hearing them loud and clear, but that wasn't their source of origin. The location that we inferred from the Doppler time histories turned out to be rather farther afield. It was coming from the Eastern Mediterranean. Specifically, it was coming from an airbase in Syria, operated by Russia. The ellipses you see here are based on the post-fit residuals. In other words, we look at the post-fit residuals and we say, what is the error in the Doppler measurement that we're able to make over the time history? And then because of that error, we are going to be off in our ability to locate the source. And then we inflated that somewhat to account also for the timing variability in the OCXO driving the transmitter. Anyway, this is where we determined the location to be. We don't know the true location, but we suspect that it's very close to this and very likely to be within this 95% ellipse. The outer ellipse is the 95% ellipse. This didn't surprise us much because looking at news reports around 2018, we found that some of the US Special Operations Command folks were saying that Syria was the most aggressive electronic warfare environment on the planet at the time. And we're not going to speculate too much about the motivations for the transmitter that was placed there, but we can say that it's rather effective at denying GNSS GPS use in that area. Now I'll turn the time over to Lakshay, and he'll talk about an expansion of our work that took into account a more global perspective. Lakshay?
Hello, do you hear me?
Yes, sounds good.
All right. So this part that Todd talked about relies on these 60-second raw captures that we're able to do from the photon receiver on the International Space Station. And obviously, it's very exciting to be able to pinpoint with, such accuracy the location of this jammer. But the other thing that we're capable of doing from this receiver on the space station is it's continuously running and streaming down observables as it's orbiting the Earth every 90 minutes. So there is another opportunity that we have, and that is to do a global survey of the interference landscape in the GNSS bands at both L1 and L2. And it's pretty straightforward to see this in the data. The chart here shows the receiver reported carrier to noise ratio as the space station is flying past the same region that Todd was talking about in Syria. And you can see that there's a clear drop in the carrier to noise ratio as reported by the receiver when it's flying over this region and getting noise from the jamming source. So this can be set up as a hypothesis testing problem, right? We can find out what the receiver reported carrier to noise ratio looks like when there is no interference. And we can learn that distribution when the International Space Station is flying over these open oceans, right? So in this chart, we exclude all land masses and some area around them and assume that there is no interference going on in deep oceans. And then we can learn the carrier to noise ratio from the receiver in these regions. And then when we're flying over land masses, we can test whether or not the observed carrier to noise ratio values from the receiver actually belong to the null hypothesis distribution, which is that there is no interference, or if it's not from that distribution. In that case, we might suspect that there might be some activity going on. Now, this is a fine idea. We can definitely go ahead and do this and get some charts, but we can do a little bit better than this. So in a hypothesis testing problem in which we only have the distribution under H0, what would be best is if that distribution is tight, right? We don't want a fat tail distribution when we're doing this hypothesis test, because we want to increase the probability of detection while maintaining a low probability of false alarm. So what we do here is we exclude some of the factors that are deterministic but affect the carrier to noise ratio, right? So these include the predictable variations due to the satellite vehicle. So some PRNs are hotter than others, and we can compensate for that effect. For the frequency band, the carrier power is different at L1 and L2 for these satellites, so we can compensate for that. Obviously, the range between the GPS satellite and the International Space Station, the antenna on the photon receiver. So that obviously affects the carrier to noise ratio, and then also the off-bore sight angle for the GPS satellite antenna, and as well as the photon antenna on the space station. So how do we do this? Well, it turns out that the off-bore sight angle for the GPS satellite does not actually affect this analysis a lot, just because of the geometry of the problem. But the other four, or at least, okay, so the range, obviously, we know the position of the GPS satellite, we know the position of the photon receiver, so we can calculate that range and, adjust for the free space path loss in that case. And the other three, the variations due to the satellite vehicle, the frequency band, and the receiver off-bore side angle, we actually learned these on the fly. So the same data that we use to calibrate the H0 hypothesis, we actually learn, which satellite is hotter than the other, which frequency band, and by how much is hotter. And then also we learn the antenna gain pattern for the photon antenna on the space station. So after we calibrate for all of these effects, our test is a lot more sensitive now. We have a thin distribution under H0, and we have better capability to flag an interference event as the space station is flying past. So these are some of the sort of charts that are showing the drops in the compensated carrier to noise ratio. So the hat on the C is that it's already compensated for all of the effects that I talked about. And green dots here are L1 band, and blue dots are L2 band. And what's interesting to see is, again, like at at this specific epoch on the top chart, both L1 and L2 carrier to noise ratio falls down as the receiver is passing over some area, which we can obviously, like, since we have the timestamp, we can find out where we were. And then in the bottom chart, we see that there is an epoch where both L1 and L2 drop, and then there is another one where, for some reason, L1 carrier to noise ratio seems just fine, but there is a big drop in the L2 carrier to noise ratio. So some interesting trends going on. And basically the next step here is to map these timestamps onto a map, of the world, and see where these events are happening, right? So we can go over to the next one. Okay, so this in particular is showing the L1 band events. So the color on this chart is how often the hypothesis test is failing. So how often the hypothesis test says that there is interference, and that's the color bar on the right hand side. And then you see that there is a big clear hotspot on the map, and there is a red dot to the left of it, right? So first of all, why is the red dot? So the dots are something that we put on just for explaining this chart. And so why did I put the red dot to the left of the big hotspot there? Well, that's because the International Space Station is flying from left to right on this chart, and the antenna is pointed aft. So the data that we are getting, or the signals that we are receiving, are from behind the space station's flight path. And the red dot actually, in this case, corresponds to the exact location that Todd mentioned in his analysis that we estimated for this, jamming device on the Russian airbase. So it's very clear that every time we are passing past this airbase, we are failing hypothesis tests, and that's to be expected since we're getting very strong interference from that region. But there is also another spot to the left of this red dot, which is intermittent. It's not as strong as the one on the right, but it's definitely more than what we would expect from a false alarm perspective. And just going by that pattern, this magenta dot that we have is something that we just put manually on there by approximation. So in this case, since we don't have the 60-second captures, we are not able to estimate very precisely the location. But given the pattern of how it shows up on the map, we estimate that this magenta dot is where the jamming source would have to be for the hypothesis tests to fail in the region where they do fail. So, and it turns out that magenta dot is actually in Libya, and it's intermittent, and it starts out of the 3 years of data that we collected. It starts towards the mid 2019-ish timeframe. So that's for L1. So, we've got the obvious spot in Syria, and then we've discovered something new in Libya that we hadn't had raw captures for, but it's an interesting fact that there is in fact more interference going on in that region. Now this chart is for the L2 frequency band, and in both the Libya and Syria region, we still see the same pattern. There are a lot of tests that fail, indicating a lot of interference in that region. So in both of those regions, the GNSS, both L1 and L2 bands of GNSS are being interfered with, which is interesting in itself, because L2 is not a band that is typically used in civilian receivers. So if there is interference going on at L2, then that's clearly an indication of of military intent or similar. But the most interesting part in this second L2 band chart is that there is a very clear interference activity going on in mainland China, and this activity is absent on L1 frequency. This only happens at the L2 band. And once again, like the green dot here is not an estimated or like it's not estimated from signals, but only from the pattern of the failed hypothesis tests that we see. So if the hypothesis tests fail in this region, then the transmitter has to be located somewhere to the left of that. And so we just put a green dot there for explanation. But yeah, that is another kind of interesting anecdote from this data, is that there is L2 only interference going on in mainland China, and that is kind of an interesting fact there. Yeah, this is another kind of interesting thing. It's always funny. I mean, I think I've never seen any of the papers that I've known being cited in a YouTube video, but it just shows the power of interference monitoring from low Earth orbit. So Clara Chu is a researcher who studies soil moisture levels using GNSS reflectometry data. And it actually turns, she uses Cygnus satellites, and it turns out that these satellites are actually much better at detecting interference than the receiver we have on the International Space Station, because the purpose of our receiver was not actually to do this, but rather for radio occultation. The Cygnus satellites have two antennas pointed towards the ground and one antenna pointed up towards the sky, and they're measuring GNSS reflectometry. So they have antennas that are directly, facing the Earth, and so their, gain patterns and everything are favorable. And she was seeing a lot of anomalous data as she was studying soil moisture in the Northern Africa region. And she happened to, stumble on our paper and, us confirming these interference events in Libya and Syria, and that exactly matched up with what she was seeing in her data, where in 2018, she's seeing a lot of noise in the reflectometry data when the Cygnus satellite is going over Syria. And then starting mid-2019, she starts to observe more and more anomalous data over the Libyan region. So it was really exciting that this independent source of information with a different low Earth orbit satellite is able to confirm our data as well. Now she wasn't able to confirm the L2 interference over China, because I think that's not that data is L2 data is not available on the Cygnus satellites. But this is like a great opportunity for us as a community to be able to verify these events and keep track of the interference landscape all across the globe. Do I have else? Yeah, okay. So I'll hand it back to Todd to continue and finish the presentation.
Okay, thanks, Lakshay. I'm just going to have some concluding remarks to discuss the implications of what we've found for GNSS receivers. And I've organized these as follows. First of all, it's just the fact that there is a lot of deliberate, persistent, unauthorized, wide area GNSS interference going on around the globe nowadays. And I think we'll have to just get used to this. It's also the case that monitoring this from low Earth orbit seems to be the best way of keeping tabs on where it's occurring and what kind of structure is built into these interference waveforms. But another more concerning point to make is that if your receiver is specially designed for spoofing detection, say it looks for alternate peaks in the time and Doppler search space, and it raises a flag and refuses to give a navigation solution if it finds a second peak, then that receiver can be said to have improved spoofing detection. But if it doesn't have also improved resilience to spoofing, then this opens the door to spoofing for denial of service. And let me see if I can put a finer point on this. What I'm saying is that it can be rather easier to knock a receiver offline by using spoofing in the way that we've talked about this. It's coded jamming, simulating a GNSS signal with the right PRN code, but it doesn't really matter if you add the rest of the modulation. It becomes more potent than traditional jamming. And to understand this, think about a receiver that has a carrier-to-noise ratio threshold, say of 30 dB hertz. So my eta variable, my eta variable down here is 30 dB hertz. Then this equation will tell you for what's called matched spectrum spoofing, where they take the spoofing signal, matched spectrum interference, where the interference waveform has the same spectral properties as, say, a GNSS sync squared waveform. And it will tell you what the spoofing power, the interference power to the authentic signal power, or the jamming to signal ratio, would have to be in order to drive the carriage to noise ratio down to 30 dB hertz. And what you find is that comparing this against a spoofing attack where you would only have to get to interference to authentic power ratio of 0 dB hertz, you have about a 32 dB gap between these. In other words, for denial of service, a 1 watt spoofer can be more potent than a 1 kilowatt matched spectrum jammer at the same standoff distance. And this is maybe what is behind the intent of the signal structure chosen by those who are transmitting in Syria, because the signal can have an effect at a much further standoff if it's able to affect receivers who are going through some sort of a cold start or are doing a reacquisition. In that case, they see multiple peaks, and having seen multiple peaks, they might not be able to distinguish those, and so they might deny a navigation solution. They might refuse to provide a navigation solution, and effectively they have been jammed by a much weaker signal. Other takeaways. Well, first of all, a science-grade GNSS receiver in low Earth orbit is a fantastic instrument for monitoring global GNSS monitoring. It's able to detect fairly weak signals on the surface of the Earth. If you're only using carrier-to-noise ratio, then 3.5 dB watts of a transmitter is possible. Whereas if you're able to acquire a signal that has, say, GNSS structure to it, then you can use traditional acquisition techniques to acquire even all the way down to, say, negative 28.5 dB watts. Then we showed that localization of these terrestrial sources is possible to better than a few kilometers. But I want to emphasize here that we got lucky in our localization. The transmitter in Syria was broadcasting a signal that had a nice carrier to it on all of the different modulated PRNs. We were able to use that carrier to infer the location from a Doppler time history. It may not be always the case. It'll probably be unlikely to be the case that jamming activity on the surface will have a discernible and extractable carrier. If it doesn't have an extractable carrier, you can still do some things with the time history of approximate Doppler that you obtain, but you may wish to resort to time difference of arrival, having 2 satellites, or frequency difference of arrival, and that is what is being pursued more recently. But in our case, we were able to locate a source to within a few kilometers with carrier extraction. We've detected wide area persistent GNSS interference in 3 different locations. And we found that this interference from Syria is matched code interference, which appears to be very potent for denial of service. Lakshay and I are happy to take your questions now, and we can go to the end of the hour and entertain whatever's on your mind. Thanks.
Great, thank you both for the wonderful presentation. If you have questions for our presenters, please use the Q&A button in your viewer, and that will put it into the queue for us to review. Lakshay, I see you have flagged a question here. We have a question, were there any other customizations to the receiver and antenna other than recording the raw IF data?
Yeah, so that's an interesting question. I think Todd answered that in his talk a little bit. Basically, there's no hardware customization. This receiver was on the International Space Station for radio occultation, but the software-defined nature of the receiver allowed us to track these special signals that don't have any data modulation on them, but still we are able to extract the Doppler time history. So there is customization to the software receiver, but no customization to the antenna. In fact, the antenna is not pointed in an ideal direction for detecting interference. But as Todd said, in this case, the interference was strong enough and of a nature that we could track pretty well. So the customization is in the software and in the tracking of the signals in this case. Yeah, thank you.
Okay, great.
I'll handle this next. I'll go ahead and handle this next question. We've got one from a friendly name, Kyle Wesson, a former student of mine. He asks whether in the raw captured IQ data, there we could extract a metric that would indicate how severe or widespread the outage would have been on the ground. And yes, the truth is that we were able to do an analysis by looking at the drop in carrier to noise ratio compared to known authentic signals and determine what the jamming power was we were receiving at the International Space Station. Then backing that out and doing an analysis of the location of the Syrian transmitter, we determined that the transmitter EIRP, so what we were seeing through the gain pattern of the antenna, was around 100 watts. And so this was not a terribly powerful transmitter, at least from our perspective, but it may have been pointed more toward a horizontal gain distribution. In any case, 100 watts would seem very powerful for aircraft or people even on the ground in the locality of this transmitter. For aircraft, it could go off 100 kilometers and still be effective at jamming using this sort of denial of service type of jamming. So thanks, Kyle, for the question. Lakshay, have you got another one?
Yeah, I've got something that maybe you should clarify. There's a couple of questions asking how the spoofer or the jammer in Syria was able to affect all of these receivers in the Black Sea. So I think that's maybe a confusion that wasn't clear. So there are two questions on that. So maybe just address that.
Yeah, sure. So this was part of the mystery that I tried to build up to in the presentation. We captured signals near the Black Sea with the intent of understanding the spoofing that was going on there. But it turned out that the signals we actually received at the time were coming from Syria. My suspicion is that the Black Sea spoofing was indeed going on, but the Syrian jammer was so much more powerful. The Black Sea signals simply don't show up to a trackable level in our data. In other words, the signal that we were receiving mostly was not from the Black Sea region. From these three traces that you saw on earlier slides, we were still able to see the airport in Syria line of sight, even all the way through these 60-second captures. So it looked like it was very far away on the globe, but at the altitude of the International Space Station, it was still line of sight. And it was those signals that from the Syrian transmitter that were actually causing the degradation and the spoofing signals that we tracked. So yeah, that mystery was solved. It doesn't mean that the activity wasn't going on in the Black Sea. It was just totally overwhelmed by this more powerful transmitter in Syria. Have you got another one you'd like to follow up on, Lakshay?
All right, so we could take this one. Could more locally gathered terrestrial GNSS spectrum data support geolocation with the data gathered from the ISS? It's from Stephen Hancock.
Yeah, so For example, if you had terrestrial receivers that were gathering data locally, you could build up a map of the interference that would supplement a LEO-derived map. The disadvantage one has at LEO is that one is, say, 300 to 400 kilometers above the surface of the Earth. And so one isn't as close to the emitters as somebody on the ground would be. However, there's an advantage of that standoff distance in that throughout the jamming that we experienced, we were still able to track authentic signals. And that allows us to know our location and our timing well enough to do localization of the jamming sources. So, you know, it's a trade-off. You'd like to be closer to better examine the signals, but being farther away allows you to resist the jamming and track the location of your own receiver.
Sweet. So there's a couple of related questions that I think I can take. So they're asking if we'd be able to detect less permanent jammers or spoofers, or do you need multiple passages to actually confirm the detection? So there's kind of two answers to that. If we had raw data from throughout the experiment, we'd be able to detect any temporary jamming or temporary spoofing as well, as long as it was strong enough to be heard up there. For the analysis that we showed in the second part, where we were doing this aggregate analysis over the years of data, in that case, it does drown out any of the temporary jammers or spoofers and only detects something that is persistent. And so, yeah, basically, if you have the raw data, then with the technique that we outlined, or the other techniques that Todd talked about in time difference of arrival or frequency difference of arrival, we only need a small snapshot of data to confirm and geolocate. But for aggregate analysis, we're only able to do more permanent and persistent activity of interference.
Thanks, Lakshay. I'll take a question from Gregory Weaver and one from Kyle O'Keefe. Greg asks whether the denial of service notion of the signal would also be effective on commercial receivers going through a warm boot. So I talked about a cold start. He's asking about a warm start. With a warm start, you have some knowledge of your location. You may also have ephemeris information and clock models for the satellites. In that case, you are in much better position because your ability to distinguish, say, a correlation peak due to spoofing from a correlation peak due to authentic signals is much greater. It sort of depends on the uncertainty in your initial location and your timing as to whether you'll be able to confidently choose authentic signals versus spoofing ones. So if you have a loose initial condition, it may be that you still declare yourself to be offline, not available for providing a navigation solution. It really depends. But if you've got a very tight timing and location and position solution, then you can more readily resist the spoofing. It's a little sad to say this. I mean, you basically have to know where you are and what time it is in order to know where you are and what time it is. But it's a bootstrapping question. You can start with accuracy and work yourself up to greater accuracy. Kyle O'Keefe asks whether we're concerned that future coded jammers like the one in Syria might dither their clocks to conceal their locations from Doppler tracking. This is a good point, Kyle. And in fact, it may be that they adopt different techniques, various different techniques to try to conceal their location. Dithering the clocks would be rather effective, but we could still get to within, say, tens of kilometers, maybe hundreds of kilometers. If they really want us if they really want us to prevent us from tracking any kind of carrier, they can of course broadcast a broadband waveform that doesn't have an extractable carrier. But that broadband waveform might not be as potent as a coded jammer for denial of service. Thanks for those questions. Lakshay, do you have any others?
Yeah, there's a couple more that are related. So these are from Angel Arcia and Nikolai Gerard. They're asking how powerful or successful do you think LEO RFI detection would be if done commercially compared to your work? And so basically, are there designs or antenna pointing directions which could greatly improve our ability to geolocate and detect these jammers if they were to be dedicated receivers doing so?
Good. And did you also want to answer Fabio Dovis's question? He asks about transient jammers, those that come and go, and whether we'd be able to detect those.
Yeah, so that's the one I addressed in my previous.
Oh, okay. Okay, that was the fun. Oh, so I want to follow up and say that I have another student working on this and is interested in seeing just how little data we would require to obtain a decent localization for these, say, more transient jammers. I'm looking at a question by Dean Passion. The 50 bit per second navigation data is saved in most receivers, and if it isn't available, the solution uses the relative time offset of the PN coding for position using the old navigation information. So do you think that spoofing is still possible even for matched code signals without navigation data? It is possible, but almost all receivers will go through a series of checks as they track a signal. And as soon as they determine the signal isn't modulated by GNSS data, it's very likely the signal will be rejected as unhealthy or unsuitable for navigation. So whereas it's technically possible, it's to obtain a navigation solution from one of these signals that doesn't have the modulation, it's very likely that the signal will be rejected by the receiver anyway. An anonymous attendee asks whether the locations that we discovered are still active and being jammed at the moment, and if not, how often they come on and go off. We're aware of, up until the last summer, we had a look at our data. We're aware of the Syrian jammer still active and other jamming going on around the Mediterranean. We also see from reports, from AIS reports, jamming going on around the coast of China, Shanghai region and other places, but we haven't confirmed that yet using the International Space Station receiver. And in other words, a lot of interference is going on, and it's plenty exciting to watch it all happen, and kind of distressing to realize that that this is being engaged in so openly and with some brazen disregard for safety.
Yeah, and last summer when we checked, the L2 interference in China was also still ongoing. So
there's a question from Wanda asking whether the jamming was directional versus omnidirectional. In our case, Wanda, we're not able to get a good sense of this because we always tend to look at the jamming sources from the perspective of an anti-velocity direction on the International Space Station. So we're not really able to get a 360 view of the jammer. We always look at it from, say, east to west and fairly low elevation from the perspective of the jammer. So a full gain pattern is not available from our own data. Let's see, Nikolai Gerard asks how powerful or successful, oh, Alexei, that's for you. Or did you already answer that one?
Yeah, I asked you to answer this one, but I think we
okay.
Messed up.
If it would be done commercially versus your work. Okay, so I'm aware, for example, of commercial activities where satellites have been put up in low Earth orbit with the intent of doing fairly broad RF analysis of interference and other, say, RF activity on the Earth's surface from the low Earth orbit. These are commercial activities using multiple satellites, so they can use time difference of arrival and frequency difference of arrival techniques, which would improve on our techniques because they would be agnostic to the waveform. They wouldn't need a waveform that has an extractable carrier in order to do location. They could also have superior antennas with superior positioning. So apart from the fact that we have a very fancy GNSS receiver that is highly adaptable and we have a lot of understanding of how to track even strange GNSS-like signals, I think commercial efforts could do much better than we have done. And you know, I applaud those efforts and think that that is seizing the opportunity and moving forward.
So I can take this one from Kyle. What does the data downlink backhaul look like in terms of data rate, frequency range, and persistence? For example, do you get a continuous downlink data, or does it come in chunks to allow for other downlink transmissions from the ISS? So yeah, we do have only limited capability to record the 60-second raw data. That is only done on demand and has to be commanded specifically every time. For the observables and the IQ data, we do log them continuously on board the ISS, but they do only come down in chunks. In fact, like several days of data comes down at once, I believe, and then is transferred from the NRL to UT. So yeah, we definitely don't have a continuous pipe from there, and we also have limited capability. So the 60-second chunk, I believe, Todd, correct me if I'm wrong, has to be downloaded before like another 60-second chunk could be recorded on board.
Yeah, that's right. In fact, it knocks the receiver offline for about a day between all of the kinds of commanding that we have to do and the time that it takes to get the data down through the network, the NASA backhaul network.
Yeah, so these are all kind of side effects of not having a dedicated interference probe. It's just a radio occultation probe in space. Yeah.
Yeah, using the science grade receiver and stealing it from its day job to do interference monitoring. James Aristad asks, it seems that much of your analysis involved turning the normal GNSS signal processing on its ear and inferring from what you actually recorded what transmitter would have created it. Are these techniques unique to space-based data collection, or would it have application on ground-based software-defined receivers? Well, one has to have, for Doppler time history-based estimation of the transmitter location, one has to have relative motion between the transmitter and the receiver. So something flying on an aircraft would work fine. In fact, it might work quite well. Something that was just stationary near the transmitter would not reveal the transmitter's location through Doppler, but say from multiple vantage points, one could maybe estimate using received signal strength the location of the transmitter. And of course, if you have multiple listening stations on the ground, you could use time difference arrival, frequency difference arrival, maybe coupled with motion profile to really accurately estimate the location of the transmitter. So it is nice, though, in LEO, you're going so fast that the Doppler-based approach works quite well, because the speed of the change in the Doppler is there's such a strong signal there that variations due to the transmitter clock are somewhat less important than they would be if you were traveling slower.
Sweet. I think you could kind of have some thoughts on this, Todd. Larry Hotham asks, could the signal from the Black Sea source be directional versus omnidirectional? That's a possible factor in why it wasn't detected at the ISS.
Yes, I think this is very much a possibility. I also think that the Black Sea signal need not be nearly as potent as the 100-watt Syrian transmitter to get the job done that we saw in those charts from the Black Sea. It could have gotten by with something even as low as a 10-watt transmitter. So yeah, the fact that we didn't see it could be directionality of the antenna, or that it was a weaker signal to begin with.
I can take this one from Fabian. Where do you see the limits of RFI detection and localization from LEO? So yeah, this is an interesting one, because I think with time difference of arrival techniques and synchronized satellites in space dedicated to detecting RFI, we could do a lot better than we're able to do in this opportunistic sense. I think one of the limits is going to be the standoff distance. If the spoofer is weak enough, we won't hear it in orbit, but it can still disrupt operation on the ground. At the same time, I mean, with the curvature of the Earth, if the spoofer is, it doesn't have to be very loud, because even if it's loud, it can't in many cases affect a larger area because of the curvature. So I think that is one of the limitations, is how do you do a better job at detecting weaker sources of interference from space? Todd, would you like to add anything to that?
No, that's a good answer. I've got one here that asks, what questions did our research leave open, and what could be the next steps? I have a student working now on answering questions of what are the ultimate limits of our ability to detect jamming from the surface in low Earth orbit based on such things as carriage to noise ratio. If we're just monitoring variations in carriage to noise ratio, how good are we able to distinguish those from the normal variations due to, say, slight multipath and whatever Lakshay was not able to model in his hypothesis test modeling for the null hypothesis. So I'd like to write a second paper that examines the limits of detectability for both full acquisition of GNSS-like signals and, say, just being noticing a drop in carriage to noise ratio, those types of different methods for detecting something going on. And B, I'd like to know better our ability to locate emitters on the ground using time difference arrival, frequency difference arrival. It turns out that there isn't much literature on the limits of locating emitters on the ground from LEO. There are other papers from other orbits, but from LEO, it seems to be somewhat poorly defined in the literature how well you could locate a transmitter using time or frequency difference arrival in multiple satellites. So I see those as open, interesting questions, not deeply fundamental questions, but interesting enough to pursue in further research. Also, Robert Corville asks, he says, given that we can determine where the jamming occurs, would it be possible to publish those locations on a map, like in real time? This might deter some users for jamming, or at a minimum, tell the aviation community where jamming is occurring. Yeah, you know, we as academics kind of have to take the slow road to this, Robert. We publish only after the peer review. And that's the way we got the information out in this paper. But you could imagine using the commercial satellites that are now up there doing something similar and offering this to the public. However, those commercial satellites are being funded by government agencies that might not want all of the information being published to the public. So you've got some trade-offs and incentives, I guess, that you'd have to worry about. And then Gerhard Bertz asks, how would you go about detecting RFI from a LEO source? So somebody put a jammer up on a LEO satellite. Well, very similar. The RFI would come up on, say, permanent GNSS receivers across the globe. The CORS networks that are being used for the IGS and other networks would tend to show a blip as the satellite flew overhead. How about locating it? Well, again, if you can extract a carrier, then you can locate it using old school transit techniques. And if you can't, then you could use time difference arrival, frequency difference arrival, or receive signal strength techniques to do something approximately as good. I would hate, Gerhard, to see the day when somebody goes ahead and puts a jammer, a powerful jammer on a LEO satellite, but maybe it's not out of the question. Lakshay, do you have any others?
Maybe you could quickly knock this one. Can these data be available publicly for analysis, or is this confidential?
The Naval Research Laboratory has not authorized us to offer the data publicly, but that may change as time goes on. The idea is that the data have to be kind of kept within the NRL partners for the first couple of years, and then when papers have been written, they're willing to open it up more widely.
Cool. Gary asks, have there been any correlation or collaboration of your findings with terrestrial reports of interference? Yes, in fact, with the Coast Guard website where you can post all of the interference events with GPS, there were a lot in the Libyan region that were reported around the same time as when we started detecting. So with NOTAMs and AIS, I think NOTAMs would be more for authorized and not very persistent events. So there has been some collaboration with you know, as you mentioned, with Cygnus data as well, and also with the Coast Guard website. Dr. Psyche has a tough question. I don't know if you want to take a go. I think even with like maybe what he's referring to is like the time difference of arrival techniques that we've been talking about. What if there are multiple sources that are simultaneously detectable from LEO?
Yeah, well, if these multiple sources have different carriers, then you could track them independently and locate them independently. But if they are just broadband noise with no extractable carrier, you might have a hard time using received signal strength techniques because it's tough to distinguish the multiple signals if they're close enough together. In fact, my student Daniel is working partly to try to understand the limits of resolution of a received signal strength technique based on, say, carrier to noise ratio, given a LEO satellite. You can imagine that something that's separated by 200 kilometers might be resolvable from just carrier to noise ratio, whereas something separated by, say, 50 kilometers might not be resolvable. But if they're emitting coded jamming signals like the source in Syria, then even very closely spaced receivers could be resolved and located independently. Angel Arcia asks how much data is generated with the 60-second data captures. So we are sampling at about 6 mega samples per second, and we are sampling 2-bit samples at 6 mega samples per second on L1 and L2. So you can work that out and find out that it's several hundred megabytes of data that we get over a 60-second capture, which is why it takes a while for that to come back down over the NASA backbone. Did you want to take any of these, Lakshay?
I can try on this one from James. Did your research provide any indication of the trajectory of efforts being undertaken by adversaries over time? Not really. We were only able to see that, for example, the L2 interference in China and the L1 and L2 interference in Syria was persistent. We only have deeper visibility from these three 60-second captures, and they were very similar and also not taken that far apart in time. So I think it was the same source over the course of those 3 recordings. So not much in terms of the trajectory of efforts. Yeah, that's what I have to say about that.
Okay, I'll address this last question from Dominic Hayes. He asks whether a high-powered jammer would impact the ability to use GSS for space service volume applications, the ones that can be applied above the GNSS orbits, because these applications have a need for high sensitivity GNSS receivers. And you can imagine those receivers being more easily jammed because they're looking for very weak GNSS signals coming from satellites even beyond the orbit. Yes, I expect, Dominique, that this could have an impact on those receivers. But I want to answer more broadly that we've already found a fairly significant impact on all space-based receivers. So those operating in low Earth orbit that transit over the Eastern Mediterranean, many of them have receivers that are, say, not as good as the photon receiver at tracking through the jamming, and they just get knocked off of the of GPS. They are denied GPS over that region. And this is of concern because these satellites depend on GPS in many cases to do their situational awareness, to know where they are in their orbit and determine whether there's going to be a conjunction with another satellite. So this is dangerous for collisions in LEO. It's also dangerous because it prevents GNSS from being used in the space service volume. And so, yeah, we'd like to see these sort of jamming events be eliminated going forward, but I guess we won't hold our breath for that. A last question from Brendan Polidori. Could multiple satellites equipped with the proper hardware overcome the problem of multiple interference sources close to each other? Lakshay, would you like to take this one?
Go ahead, please.
Yeah, so Brendan, most importantly here is that time difference of arrival techniques can have a much better resolving power than received signal strength techniques. If you're using time difference of arrival, you're basically making 2 recordings of a signal from 2 different locations with time synchronized clocks. And then you can cross correlate those recordings, and you'll see multiple peaks associated with, each peak associated with an emitter on the ground. And by taking several overpasses and looking at a time history of these things, you can resolve even fairly closely spaced emitters on the ground and quite high numbers of such emitters. So TDOA is really a much more powerful technique than using a single receiver on, say, a single LEO satellite, like was our case with the Photon on the International Space Station. The commercial efforts, as I understand, are using multiple satellites with TDOA and FDOA techniques. Well, we want to thank you all for staying a little longer, and we turn the time back over to our ION hosts to conclude. Thanks.
Thank you both so much. This has been a great presentation, informative Q&A, and we appreciate you for sticking it out here and answering all these questions. As a reminder, the video from today's webinar will be posted to our website at ion.org, along with the full paper that you can read and download free of charge. So we thank you all. Please enjoy the rest of your day. And again, you can find all of this information online at ion.org. Good day.